Thanks very much for the invitation. It's really an honor. So I'm talking about convex cocompactness in mapping class groups via quasi-convexity and right-angled arc groups. There's a lot of words there, so hopefully as I go through the talk, we'll get to all of them. And this is joint work with Sam Taylor, who's a graduate student of Alan Reed's at the University of Texas. Okay, so what do I mean convex cocompactness in mapping class groups? I'm going to start by telling you what people often mean. People mean when they talk about convex cocompactness in its original context, which is Kleinian groups or groups isometries of hyperbolic space. So specifically, finitely generated discrete subgroup of the isometries of hyperbolic space. I don't know if you're observing this, so I think of it as pi one manifold. This is convex cocompact, if and only if, well, the name comes from having the manifold having a convex core, which is compact, but there's many equivalent ways of describing it, and the two that are relevant for the mapping class group definition, or there are multiple ways that are relevant to the mapping class group definition. The two that are relevant for this talk are first, if some orbit, so you have a group and it's acting on hyperbolic space by isometries. So if some orbit is quasi-convex, that's an equivalent condition. And I'll remind you that quasi-convexity is almost like convexity. Take the geodesic between any 2 points in the orbit, and rather than running through the orbit, which you wouldn't expect anyway, it runs a bounded distance from, so a quasi-convex set, a geodesic between any 2 points in that set stays a bounded distance away from the rest of the set. So that's the quasi part right there. And you can do it with one, you can do it with any, so make that a double statement. Equivalently, you can require that some or any, so we're looking at the orbit again, and then this time let's think about the way that the orbit maps into so we think of the group as a space, like we take a Cayley graph for a group where we pick a bunch of generators, so we have a word metric. So we look at where it takes the point, and that maps the group into the space. And we require that that's a quasi-isometric embedding. And what this means is it's not quite an isometric embedding. Rather than have distances in the group preserved on the nose, which wouldn't make sense if I was vague about what metric I picked on the group anyway, we just require distances to be preserved up to some fixed additive and multiplicative error. So that's the quasi part right there. Okay, so these are what it means.
You have to choose constants for all of those.
Oh, that's right, yeah. So it means there exists a constant that this is true for any 2 points in the quasi-convex. And then quasi-isometric embedding, you'll have an inequality that works for any 2 points that you pick and their images, and then the constants will be chosen at the get-go, and the inequality works for any 2 points. So, sorry, I'm talking over it to avoid writing it out, but it's like an isometry for quasi. That's true. This is good enough. All right, so a classical example of these convex cocompact groups, what's an easy way to get a bunch of them, or classically anyway. So here's hyperbolic space, and I'll do this ping pong construction of Schottky groups. So what you do is, you take 2, or if you're in a good mood, n, hyperbolic isometries, and I want them to be actually independent. And I'll show you what's a good enough for me definition of what independent means. So So you know how hyperbolic isometry acts in hyperbolic space? It translates, in particular there's some axis that it translates along the axis and everything gets dragged along. Everything gets dragged along as it would. So let's call these F1 and F2. So maybe here I draw the axis for F1, and maybe this is the axis for F2. And I got to fulfill this definition here, so I can take any base point for my orbit, and I'll take a convenient one here. I'll take this one. And what's true is, okay, so maybe this nice construction isn't going to work with my arbitrarily chosen hyperbolic isometries, but if I crank them up a bit, I choose a big power so that the amount that they translate along their axis is sufficiently huge, sufficiently large, A. Then I look at that, the group generated by those. Well, what happens? So this is a familiar picture of something you saw drawn yesterday. So this point right here, so I'm looking at its orbit under the group, and F1 is moving it very far along its axis, so far that it translates this axis really far away, so these are conjugates of this axis. And I keep asking so what about other elements of the group? And I write various words in the group generated by these two elements, and I look at where they're going to be. Maybe I can start out by moving along this axis first. So you see what I'm drawing here is, looks like it's a tree. And the point is, if these axes are, if this translation line is long enough, these points are really far apart, and like you'll have some kind of local to global action in hyperbolic space. These angles will be, this points will get farther and farther away as the word gets longer and longer. So overall, the distance in the word length is roughly the same as the distance in hyperbolic space. And this tree here, which is the Cayley graph or the free group on these two things, is quasi-isometrically embedded in hyperbolic space. So this is your classical convex cocompact Shuffy group right here. Okay, so now let's do the definition in the mapping master.
So where does the cocompact enter here? I guess the trivial group also, is it also satisfied one and two?
Sorry?
So in the definition, where does the cocompact show up in the two?
Oh, okay. So then you, well, let's see. One way to do it is you.
Does the trivial group satisfy the two conditions?
Yeah, it does.
It's also called cocompact.
Okay, so what the thing that's cocompact is the convex core of the manifold corresponding to that group. So you
Is the empty set compact?
okay, I don't want to deal with things like I don't know.
Okay. I just don't see the cocompactness as a definition.
Well, it's the convex core that's compact, not the whole quotient.
There's an alternative definition where you act co-compactly on the convex whole limit set.
Yeah, so you take the limit set and then you connect all the points in the limit set by this infinite geodesics, and you keep doing that and you get this convex hull, and that's going to be, you know what's relevant to the, it's kind of, maybe you'll remember it for later, but there's going to be a convex submanifold of a convex subspace of this H3, which the group actually restricts to, and then you can, and then if you take the quotient by that, you get this compact thing, and that thing is actually going to sit in the, it's going to actually sit in H3 mod G. It's going to carry the fundamental group, but it's going to be convex, and it's going to be convex in there because it's this convex space here, and that's what's called the convex core, and the cocompactness is that core being compact.
Convex cocompact is a single word. There should be a hyphen or something.
Yeah, it's not convex comma cocompact. It's a full.
It's convex cocompact.
It's a property of.
Yeah. So Z is definitely convex compact if it's acting by Loxodronic.
Okay.
Okay. Thanks all for all the perspectives I have Okay, so in mapping class groups, this definition is, and its justification, why it's meaningful to call it convex cocompact is due to a Farman motion, and this says that I only want to think about finally generated groups. So a mapping class group of a surface is already a discrete thing, so there's no other condition there. A finally generated discrete group, group in the mapping class group here is, I should underline it, it's a single phrase, if and only if sum for any orbit of G is quasi-convex in, so the relevant place where they use the mapping class group acting by isometries is type Miller space, which has properties very unlike hyperbolic space. So if you don't get, so in general, if something has properties like hyperbolic space, then these two things, for hyperbolic reasons, are equivalent. But you don't get that in this case. And they named it convex cocompactness because they proved that this condition is equivalent to the convex cocompact definition involving taking the convex hull and then the quotient of that being compact. You could define a weak hull in type Miller space and have kind of similar properties. It's kind of, that definition is kind of complicated. An equivalent state to this requirement is I'm going to map somewhere, but now I'm going to map into, I'll write down words, the curve complex, which you heard a bit about yesterday. So I now look at the way G maps into the curve complex, and this we want to be quasi-isometric.
What metric do you use in type Miller space, or does it not matter?
Oh, no, I think it does matter. This is the type Miller metric. And the equivalent, this is the original definition here, and the equivalence between these is due to Convex and also Latimer. Okay. So there are plenty of these, and I want to show you the plenty of examples. So, remember, so actually I'm mentioning this, but we're going to spend most of our time involving with this, which you heard a lot about it from Saul's talk yesterday. In particular, you remember Mazur and Minsky originally proved, and then there's lots of nice other proofs of that now, that this simplicial complex here, or if you want, you can just use this one skeleton and think of it as a graph. This is delta hyperbolic or Romanov hyperbolic, which for now just means that it has qualitative properties like hyperbolic space. In particular, you can run this argument again and get tons of examples of this. So what do you do? So instead of being in the hyperbolic space, now my general blob is the curve complex, and I'm just representing it, but just imagine. And I start out with two pseudo-Anosovs, and I want them to be independent. Well, first of all, pseudo-Anosovs are the right analog here because these have infinite diameter orbits in the curve complex, and if I just take the Earth orbit of some point, I can actually draw out what isn't quite an axis. I'm going to just call it it's a quasi-geodesic axis, or just call it a quasi-axis for short. To give you an idea, it's just a squiggly version of the original group. But everything else goes through because this argument of quasi-isometric embedding just used the hyperbolic qualities of hyperbolic space, so you can run the same argument again and take a sufficiently large power and generate a convex cocompact subgroup of the mapping class group. Well, I'll credit the existence of all of these to Farb and Moser, but this elegant hyperbolic way of proving it is described by Ken Leininger in their paper where they show that this is a way you can think about convex cocompactness in the mapping class group. Okay, so there's plenty of those. There's plenty of convex cocompactness, convex cocompact groups of that form. All right. Okay, so I want to make some remarks now. So you've heard a lot about pseudo-Anosovs. Well, you've heard some about pseudo-Anosovs. So an element of the mapping class group so I'm just reminding you of this famous Nielsen-Thurston classification. Well, it could be pseudo-Anosov, which I'm going to abbreviate PA for pseudo-Anosov. If it's not pseudo-Anosov, and it's also not finite order, I think Jesse mentioned this in his talk, then what happens is it fixes some curves. I'll just write it like that. Okay, I'll say a finite set of curves. And these are so-called reducibles. I'm just calling that to your attention because then you can, if you recall, in the curve complex, edges correspond, I'm sorry, I don't want the vertices first. Vertices correspond to loops in the surface or simple curves. And simplices correspond to this joint, simple curve. This one and this one, maybe. There, that's a two simplex that's in there. So in this definition, you can actually, if it does fix a finite set of curves, and I can improve that. This is an exercise. You can make sure that they're disjoint curves. So immediately, you see that if you're not pseudo-Anosov, in any of these two cases, you will have a bounded orbit in the curve complex. So this implies and my point, calling that out, is just to remark that it follows from this second characterization of the property that if you have a convex cocompact subgroup of the mapping class group, then all infinite order elements are pseudo-Anosov. Because if you take a high power, then we should be going a far distance in the group, but you're not going a far distance, and so you're failing the quasi-isometric embedding part. Okay, so keep that in mind while I point out what Farb and Moser were doing with their original definition of convex cocompactness. So they were thinking about extensions of surface groups, and you have a lot of these. You can always get these. The reason why is there's this beautiful, famous exact sequence to John Berman, and it tells about the difference between the mapping class group of a surface if you poke a hole in it versus the mapping class group of a surface without that hole. The only difference is are the loops, the essential loops in the surface. And these actually, this kernel here is a subgroup of this group called the point pushing subgroup. And these are mapping classes that take this point and drag it around the surface along with the fundamental. Anyway, I just wanted to give an idea of where that came from. But once you have this, take any group in here, and you can extend it to a group in here, and what they showed is that this group here is Gromov hyperbolic. So I'll remind you again, this group is a metric space with some word metric, and it turns out for this property, it doesn't matter which word metric. And this property that gives you these, that makes you like hyperbolic space is only this delta slim triangles condition that Saul drew so nicely yesterday. Triangles in the group look skinny like that. Okay, so this is a really important property about groups, and it turns out that this happens. If this happens, then G is convex cocompact.
So G here is a subgroup of mapping class group,
Yeah, right.
and you're chopping, yeah?
Yeah, that's right. Of this map, and then this one is in this mapping class group. Yeah. And then they proved the reverse direction in the case that G was a free group, and then Mensch got the complete case. So this is an if and only if. And one thing I like about, one thing I always like to point out about this, is what it means in the case that G is a cyclic group. So when G is just a cyclic group, this extension right here, this is the fundamental group of something that we've been hearing about also, which are these nice mapping phi, or these fibered free manifolds, such as cross-I, glue by phi. So this is the fundamental group of this, and we know, so if you make a special case of this, this is hyperbolic in the sense of admitting a hyperbolic free metric, if and only if this gluing map is pseudo-Anosov. We recognize that as Thurston's theorem, which came up also. And that's why I'm pointing out, a cyclic group, when is a cyclic group convex cocompact? Exactly when, by this observation here, exactly when this element is pseudo-Anosov.
Does that mean that they give you a weak version of Thurston's theorem, basically just a group theoretic version?
Yeah, well, it's also more general, so.
Yeah, but it's
yeah.
a special case.
Yeah, so this is like a group theoretic way of thinking about this, and then applying it to other things.
Do you need the Barr-Munter result to conclude that those group extensions were hyperbolic, or does it follow from something like this phenotype?
Oh, wait, which one?
The assertion that if you start with the pseudo-Anosov, that the group extension you get is work hyperbolic.
No, for this one, for the small version? No, I don't think you do. No, it comes from, you can get it from this theorem. Because if it's hyperbolic free manifold hyperbolic, then it's going to be more hyperbolic.
Right, no, I'm just wondering, if the weak version doesn't follow, or does just the group
yeah.
theoretic statement follow from this, or does it?
No, but just the group theoretic statement follows from this also. Because the alternative is that you actually fix a curve and then you find a z plus d and so you're not hyperbolic.
Sure. No.
Yeah. Okay. So the point of the talk is to just share with you some other examples of convex cocompact groups. So I'll tell you the ones that I'm aware of. When Barr-Munter first described these, well, they didn't do a ping pong. Maybe it was also ping pong. I don't know. I shouldn't call it because there's nice counterexamples where ping pong isn't good enough. I'll just write it like this. There's this first kind that I told you about right away. K1, N. These are built out of pseudo-Anosovs, and the Ki's are sufficiently large. Another thing you can do is you can take a finite group, and then you can take a conjugate of a finite group by maybe the same one if you want to keep it simple. It doesn't have to be the same. By a really in my mind, you conjugate it so it's super far away. So this is by pseudo-Anosov, and then you take K large enough, then what you'll get is you'll get a free product of finite groups that's also convex cocompact. These examples will do a min.
It's a finite subgroup of mod of S.
Yeah, that's true, right. So the theorem is you take a finite subgroup of a mapping class group, and you take two finite subgroups, and then there's some condition on F, you don't want it to be especially related to these two. So some minor condition, reasonable condition on F when a really high powered, then this group is going to be a convex cocompact. So this is some G. A cool source of examples that's recent is if you within these you look within these extension groups, and you look at the case, the case where they actually are hyperbolic. You look in these, and you look at subgroups. You look at subgroups of that, and then you require that it be all pseudo-Anosov, and you also require that it be quasi-convex subgroup. And in that case, you get that G as convex cocompact. This result is due to.
There's two G's there, is that meant to be? There's EG and then there's G subgroup of EG?
Yeah. Oh yeah. This is a new G. That's true. I used the old G.
Yeah, G's a quotient of EG, right?
So no, I mean to say that you look at now you're looking here for groups. So you have a subgroup of here. So you make some of this with use some G to make some extension reflections. Now you look at all the subgroups of that, and then you can tell if those subgroups are convex cocompact in the case that they actually are also Anosov and they're quasi-convex. This is due to Dodo chemical linear, and this generalizes this result where you just look at the subgroups of the push pi 1 of S itself, thought of as the push map the function mapping class group. So that is Kant linear Schleiner. Okay. And the so the examples that I wanted to talk about here easy to say in writing. Well, I'll fix this later. I'm just going to write the loose version here. So there's more examples. This is like the last bullet of that list there, which is, I want to write it parallel to that. So if now I have another context, what I have is, so I have to explain these things. I have a group which is also like an ambient, it's also some subgroup of a mapping class group, not necessarily functional. And what it is it's isomorphic to a right-angled Artin group in a useful way. So I'm going to call that miscible. And I'll tell you in a second what these right-angled Artin groups are. If it's one of these, so again, we're looking at some subgroup of some group with control, which you have control over that's in the mapping class group. And it happens that if this is if H is quasi-convex that in a second. And all pseudo-Anosov.
Quasi-convex in again or quasi-convex in mod?
I know. So let me fix that. But I just writing out roughly first. Then it's convex cocompact.
In
And-
mod, right?
Yes. In this context, this is the only one that makes sense. There, I meant convex cocompact in the mapping class group, I hope I said. So these are all examples of mapping class groups that are convex cocompact.
Do you know such examples?
Oh, tons, yeah.
Yes?
Right. Yeah, I mean, so this is an existence, and I'll maybe give specific examples. Okay, so what does this mean? So I was talking about this being about metric spaces, but there's something tricky here, which is that what's the metric on the subgroup? So, so first of all, the more primitive, basic question is, I mean quasi-convex in the right-angled Artin group, and if you know about right-angled Artin groups, you're thinking, what do you mean by that? So I mean with the word metric on H, and as a subgroup of A gamma, but it matters. With the word metric in A gamma, and the generators actually matter. So whether or not you're quasi-convex is going to depend on the generating set you pick for A gamma. So I mean with respect to the standard generators for, and I'll show you what those mean right now when I say what a right-angled Artin group is. Okay. So, but just to say the parallel between this and this, for example, or the general idea of what's going on. You want to know when you have this nice property for subgroups of a mapping class group, and you look in some kind of defined setting. Like here, you're looking at these extension groups. There, you're looking at certain right-angled Artin groups, and you find that what you need is some kind of property in there. And because you have some tools in this group, and I'll just point out as a saying ahead. So here, of course, you have hyperbolicity in here to work with, and here, a right-angled Artin group actually is a cat zero. It acts on a cat zero cube complex, and that's what's going to be useful. So we have non-positive. We have this phenomenon about non-positively curved cube complexes here. That's really useful. That hopefully I can sort of gesture towards
Does
what's going
every
on.
right-angled Artin group embed in the mapping class group?
Oh yeah, these are. So these are embedded.
I said, does every right-angled
Oh.
Artin group embed
In some mapping class groups,
in
yes.
some mapping?
Right. Okay. So, okay. Let me say what those are. So what is an A gamma? So, a right-angled Artin group is just any group with a finitely presented group that has a presentation that looks just like this. It's got some generators, and the relations are that some of those generators commute, and that's all. Maybe some means none, maybe some means all. That's free groups and abelian groups, and everything in between. So these are also called partially commutative groups. They're also called graph groups because you can encode this with a graph. You think of these generators as vertices of a graph gamma, and then if they commute, then you say that that means that in the graph, those two vertices form an edge. Okay, and there are lots of ways to embed them in mapping class groups. I'm just going to mention a few names, and I might be missing all that are out there. So, Paris, Greece, Roberta. But I want these embeddings that come with some good machinery. So I need to tell you what these admissible embeddings are. And that is going to involve subsurface pseudo-Anosovs. So I'll make a definition for you. By a subsurface pseudo-Anosov, what I mean is not an honest pseudo-Anosov. It's a reducible element, but it's like a pseudo-Anosov. So here's a surface S. This is the whole surface S. And here is some subsurface of it. I'll call it X. And by a subsurface pseudo-Anosov, what I mean is that I have some mapping class, but really all of its action happens on the subsurface. And if I only look at the subsurface, I would get an induced map in the mapping class group of the subsurface, and I want it to be pseudo-Anosov there. Okay. So that's what I mean by subsurface pseudo-Anosov. And
Does X have to be a strict subsurface, or can you take subsurface pseudo-Anosovs that are actually pseudo?
yeah, so by the definition, I didn't disinclude those, but I'm going to state it there and just going to put some more conditions on there. So in practice, it is going to be subsurfaces that are strict subsurfaces in the place where I'm using it. Okay, so a specific source of these admissible embeddings is a theorem with Matt Clay and Chris Leininger, which is one of these ways of embedding. What you do is you start out with some of these sort of things. Subsurface pseudo-Anosovs, and they have corresponding x's, which are connected, which are not nested, so one of them doesn't sit in the other. So if you want your group to have more than, if you want this list to be longer than length 1, then you need this, because that's nesting. So what can you do? So, well, here's A group. A right-angled Artin group, and let's say that we have the commutation. If so, I have a vertex for each of those xi's. Now you can convince yourself by imagining this picture that if I have two mapping classes supported on disjoint subsurfaces, then they're going to have nothing to do with each other, and so they'll commute. So certainly, that gives me a homomorphism into subgroup of the mapping class group if I just map all of these vertices into these FIs. And what happens is, if I crank up their individual translation lengths on the subsurface, so I put some high powers in here, then you get actually that. So this is a subgroup of the mapping class group, and you get that this induced map right here is a quasi-isometric embedding, so that's one useful thing. And that implies that this is actually a homeomorphism. So these are the right-angled triangles embedded in the mapping class group. Now,
So does admissible mean comes from this construction?
okay, so I don't want to say what admissible really means. Admissible effectively means come from this construction. There's more things that don't come from this construction, but it's really because what we really prove, the technical thing that's proved here, is that you get all this data involving subsurface projections, which Jessica talked about yesterday. And so if you list out like the properties that you get with subsurface projections, that's admissible. But you know, here's a bunch that you guys saw. That's good enough. Okay, so then here wanted to make this. So actually, this statement is a bit stronger than what I wrote here. So if you are admissible, which means one of these, so these are admissible, and then some broader group are admissible that just fulfill the technical things that these fulfill. I should say that those technical things are exactly what give the result here. So if you have one of these, and you have this, then this is an if and only if statement. Okay. Now, some people have seen this, so I wanted to bring up something new about. So I have a little bit of time, so maybe I'll try to say that, and then see how much time I have to mention all of the nice tools that come up in the proof. I don't know if I'll get to that, but it'd be nice to because they relate to other talks in this conference. But one thing that's different is, so here's an application. So there exists convex cocompact three groups generated by pseudo-Anosovs. So what's the special thing? With rather short translation lengths. Oh, what do I mean translation length? I mean in the curve complex. So this is an asymptotic thing. Let me define that. So if I have P in the mapping class group, what I do is I look at how far it moves a point in, so this is any point will work in the curve complex. And I actually take high powers and I see where that point goes. I divide out by n and I see what happens. And this limit makes sense, it exists, turns out. And this is what I mean by translation length in the curve complex. In particular, B is pseudo-Anosov, if and only if this is not zero, strictly greater than zero. That's immediate from the definition there. So if you think back, I don't know if I have it up here anywhere. If you think back to this picture, we relied on having really far distances in the curve complex, and the point is that this is going to rely on relatively short. Okay, so how short is short? Well, Badger and Tsai proved that the shortest you could get is like 1 over the genus squared. That's the shortest that pseudo-Anosov can translate on the curve complex. And I'm going to actually show an example of this that relates to, that turns out to also show up in these groups here. So that's going to be the specific example, I guess, that I can share.
So maybe I'm getting a little lost. So the point is that in lots of the examples you showed, the first thing you do is you take a really big power. And so,
Yeah, right.
so that won't work here. There's definitely not, you're not taking big powers here because they still have short translation.
Well, we're taking big powers over here, but those don't make
No.
Right, yeah. So
cool.
yeah, so those have long, and also, for example, in your theorem that I mentioned, in the push map, I think it was shown this year that translation lengths of pseudo-Anosovs in the push map are at least 1.
Mm-hmm.
So that's also okay. So I want to draw an example of something that's going to have this translation length, and it's going to be based on. So Petter had made these original examples, and lots of people have done things based on them, including these also appear here. So we're going to make use of that sort of general idea. So here's a surface, here's a big old genus in the middle. Then there's some more genuses over here. Maybe there's n of them around here. I've got another once punctured torus here. So I'll call that x0. And I'll say that f naught is one of my subsurface pseudo-Anosovs on x naught. And I'm going to make a 4 punctured, well, punctures and boundaries I'm not worried about, but 4-hole sphere here. And I'm going to call this guy y naught. And g naught is going to be the pseudo-Anosov on y naught. And then I'm also going to have rotation this way. So rho is rotation by one click, where there are 1, 2, 3, 4, 5, 6 possible clicks. So rho is a rotation. Rho to the n is the identity, brings you back to where you started, and n plus 1 is the genus. Because this one is not part of the n. Okay, and one of these short maps is going to be let B be rho g naught f naught, and then it happens that this is one of those. And how do you know that? Well, the real reason, what you really do is you take its nth power, and you show that that one, this is easier to see, has translation length like 1 over g. I just want to point out to you, oh, I didn't even say what p was. No, I didn't. I said it on there. So what is that nth power? So p to the n is equal to rho g naught f naught to the n, which you can rewrite as rho g naught f naught rho inverse rho squared g naught f naught rho minus 2 dot 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 all the way to rho n g naught f naught rho to the minus n. Of course, this is just identity right over here. Oh, I'm sorry, I didn't think about this. So you can rewrite it in such a way, I'll just look over here, that this is equal to, but I'm naming these new maps here, g1, f1 times g2, f2, all the way times gn, fn. And what are these gi's? Well, I have a clue here. Here's x naught. So this one's going to be x1, this one's going to be x2, dot, 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 and over here we have xn. And I'm going to have 4-hole sphere here, and this is going to be y1, dot, dot, dot. I'm going to have a lot of these all the way around. And the last one here, this is going to be yn. So now I can just change my definition here. What you can see is GIs and these FIs on these subsurfaces here, and these are fulfilling the conditions here. So what you can do is you can, by possibly cranking up the powers on G naught and X on F naught, you can arrange for all of these guys to be an admissible embedded right angle argument. So this is a subgroup of the mapping class group, and actually you can ensure that it's a right-angled arc group coming from this construction, right? Okay, now you can think about, well, what was this now? This was phi to the n. And so I have to leave it to you to ponder how you can see that this is, if you start with a curve in here and you apply iterates of this, you're going to need like g over 2 iterates to get that curve to even intersect itself. If the curve isn't intersecting itself, you're not moving anywhere in the curve complex. So this actually is relatively, this is rather short. This is what I mean by rather short. And you can sort of generalize. I was already cranking up powers as I desired, so I can make high powers here. And I can take powers before doing this, before taking the whole thing to the nth power. And I get a bunch of these. And what we show is that I can take as many of these as I want. So, but I want the multi-positive. I don't. And this one right here, well, the theorem is that this is going to be one of those, that this is going to fulfill the conditions in that theorem, so this is going to be a convex compact. So this is a particular example of a convex compact group, but a nice one in that it's got this funny property of rather than mapping into the curve complex with large distances, it's actually really scrunched up and spiraled up as much as you as.
How does tau come into this definition?
Oh, this here, that's my notation that I decided to use for a curve complex, asymptotic stable length, or the asymptotic translation length in curve complex.
So is the point that it suffices to have big translation length in the subsurfaces, and then the product is going to have short translation length and a whole big surface while still being convex cocompact?
Right, yeah. So that's the point, yeah. So what you have to do is you have to verify that you actually are, you do have the quasi-convex property. So I guess I want to, I haven't said anything about where this comes from. So I just want to give a couple of hints about the ingredients for, where's the, okay, the theorem's there, so I can put some ingredients here in the last minute, just because maybe you'll hear about them. And you have heard of one of them, so here is maybe in a minute, just to show what goes into. Ingredients of the proof of that theorem. Okay, so what is the upshot of quasi-convexity work, of that sort? What do you get from that? Well, there's a theorem of Hablum. So I already kind of mentioned that the useful thing about this right-angled arc group is that it has this natural Q complex that it's acting on. So, okay, I'm going to stop now.
Sorry, I'm not sure what you said.
Maybe we can talk later. Okay, so maybe I'm out of time to describe precisely the cat zero complex, but I'm gonna. Going to say in words, I'm going to denote it by this, and what this is So the one skeleton of this is the Cayley graph of the right-angled arc group. What you do is you take the Salvetti complex for the right-angled arc group, you invert that, and this is just the universal cover. Okay. So Hadlin is a theorem that's much more general than what we're using here, but I'm just going to state the right-angled arc group application. And I'm going to use this word quasi-convexity terminology that I've been using here. He has lots of quasi-convexity types. But anyway, equivalent to this, to the condition there, is the existence of a cubical subcomplex of this which is invariant and compact under G. And the upshot of that is that then you have this compact cube complex, this C modded out by G. And what's going to happen is that loops here are words in G. And the other main ingredient, which is just hidden in this two-word phrase, key subsurface projection. I'll just say it since I'm out of town. I just came from out of town. That's my excuse. Way out of town, like overseas. Jesse mentioned this this fact that if you have two points in the curve complex that have a really far distance on a subsurface, then the geodesic connecting them is constrained to run near the boundary of that subsurface. The geodesic, the full curve complex geodesic has to run near, through curves that are disjoint to that subsurface. And there's a stronger, so specifically we're using this Mazer-Minsky machinery, including the bounded geodesic image theorem, which has a nice, what's that word? Proof with a uniform constant due to Richard Webb, which came up, so I wanted to mention that. Anyway, we use that to talk about, we use that to know that in the curve complex, your orbit has to go through certain points, and then the real key is linking those points that you're stuck going through in the orbit in the curve complex with what the loops are doing in this cube complex here. So I know that was just a blurry notion of what's going into the group, but at least I got that much out. Thanks very much for your time.
Questions?
Thank you, Johanna.